So every piece of equipment that is connected to the internet, a computer, a fax machine, a cell phone, a mobile phone, has a unique identifying number that could be used as an address that the machines can network to each other and talk to each other on. And it's called the Internet Protocol address for that machine. So what I'm going to focus on really is the concept of an internet, an IP address. But I'm going to focus on what's called the IP version 4, which is the one that's mostly being used on the internet today, but it's slowly being replaced by IP version 6. So a little bit of the history on IP version 4. The idea is that we're going to use 32 bits to uniquely identify every piece of equipment connected to the internet. A little bit of a history of it, when it got started, and then how it's about 6% of the, by 1985, 6% of the addresses were used. Then by 90, 5 years later, it kind of doubled to 12 and a half, 13, then it doubled to 25, then 50. And it looked like about 2005 we were going to run out of IP addresses. So you might wonder, how many different addresses are there if you have 32 bits?
2 to the power of 32.
Right, 2 raised to the power of 32. And if you remember, 2 to the 10 bits is 1K, 20 bits is 1 meg, 30 bits is 1 gig. And then every bit you add to that doubles the previous number. So with 30 bits, we have 1 gig. With 31 bits, we have 2 gig. And with 32 bits, we have 4 gig. So with 32 bits, we have a little over 4 billion unique addresses. And when the internet was first coming out in the 80s, they thought that was way too many. We'd never use them up. But if you think about it, did you Google how many people are in the world?
Yeah, 7 billion.
A little over 7 billion. Okay. So 7 billion people in the world, if half of them had one device connected to the internet, we just about run out of numbers. So, and many people have many devices that are connected. So you would have thought maybe we would have run out a long time ago. And actually, the reason why we didn't is something we'll get into later on in this talk, but there's ways that many devices can share the same IP address. But the fact that we are running out of IP addresses is we're going to a new format. Which is called IP version 6, which is going to use 128 bits, so that'll have plenty of bits. You might think all we really need is one more bit, 33 bits, and we'll have 8 billion, which would be good for another couple of years, but they're going to go to a 128K format. Okay, so just a brief definition of what is a protocol. It's just kind of the way 2 machines talk to each other, or 2 people. Someone calls you on the phone, you pick up, you say hello, they identify themselves, conversation starts, so it's basic protocol. And on the internet, we have an internet protocol, so just throw up some definitions. Okay, so the format for an IP4 address, like I say, it's 32 bits. So with 8 bits, you can maintain a binary number between 0 and 255, right? So we're going to take the 32 bits and break them up into 4 8-bit numbers. And then because we're human beings with 10 fingers, we use decimal as our number system. We'll write out the 4 numbers as decimal numbers. So it's going to be 4 numbers divided by a period. And each of those numbers can be anywhere from 0 to 255. So here's an example of an IP address. 1 dot, and then the decimal number 160 dot, the decimal number 10 dot, the decimal number 240. So all of these numbers are between 0 and 255. But this IP address, if you wanted to write it out in its 32-bit format, it would be the 8 bits that represent a 1, and the 8 bits that represent 160, right, which is 128 plus 32. 128, no 64, 32, and then all the others are zeros. 10 written out at an 8-bit number is 00011010. That's 10 in binary. And then this is 240. So these would be the bits for this IP address. It's basically just 2 different ways of writing the same thing, writing out a 32-bit number. You could write it out as 4 decimal numbers between 0 and 225 each, or you could just write it out as their bit address. Okay? So now I'm just going to go off a little bit on a side conversation, but this is actually very related to IP addresses. So this would be a topic maybe in your computer algorithms class. You might get a question on data compression. So suppose, for example, you were sending a message from one computer to another computer, and the message only consists of letters A, B, and C. Okay, so you're sending, let's say for example, you're sending a message A, B, A, B, A, C, C, A. Okay, and you have to send it using binary number, bits, zeros and ones. So what's a way we could send this?
Can I assign numbers to the letters?
Right, we could assign numbers to the letters, so how many bits do we use for each letter? What we could do is we could say log base 2 of the number of letters we have. We have 3 letters. So we're going to say log base 2 of 3 and then round that number up. So for example, if we only had 2 letters, we could use 1 bit. 0 means A, 1 means B. If you go to 3 or 4 letters, you need 2 bits.
Yeah.
And then if you go anywhere between 5 and 8 letters, you need 3 bits, right? Okay. So obviously I picked 3 to make it difficult. So we're going to use 2 bits. So we could say, okay, 0, 0 is A, 0, 1 means a B, 1 and a 0 means a C, and 1, 1 will never be used. Okay, so now we can send the message. So here's our message, A, B, A, B, A, C, C, A. A, B, A, B, A, C, C, A. Right? It's a 16-bit message. We have to send 16 bits to send 8 letters, because each letter is 2 bits. Okay. Now, suppose, for example, suppose you noticed in your message, so we actually get to read the message before we send it, and we notice that 50% of the letters are A's, and 25% of B's and 25% of C's. Is there some way, and we have to send bits, is there some way we could send the same message, and the person who receives the message understands how to decode it, that we could use less bits? Is there any way we could use less bits? Taking into account that 50% of the letters are A's and 25% are B's and C's. So kind of a hint would be half the letters are A's and half the letters are not A. Right? B and C means not A. So is there any way we could say, you know, 1 bit means 1 letter and another bit means, you know, not that letter? Any way you could think we could compress, make the data smaller, send the same message, but use less bits? So if we notice that 50% of our letters are A's, what we could do is we could say, okay, every time you're about to read a new letter, you kind of come to the top of the street. If it's an A, we'll use 0 to mean an A. And so therefore, if the first character we see, the first digit is a 1, what does 1 mean? Well, 1 means not A.
Yeah.
Now, if it's not A, and the next bit is a 0, that means we'll let that be a B. And 1 means not A, and the 1 here means C. So now, if you start reading bits, if the first bit you read is 0, that's an A. If it's a 1, that means not A. And then you have to look at the next bit to see if it's a B or a C. So using that, we can have this assignment. 0 means A, 1, the first digit meaning not A, and the 0 means B, and the first digit here is 1 means not A, and the next digit is C. So we can use less bits. Now the message is 0, 1, 0, so it's A, B, A, B, A, C, C, B. So the person reading it sees the 0, and they look at the tree, and they say, oh, that's it, it's an A. You see a 1, that means, okay, not A, I need to read the next letter to figure out what it is. Once I get to the next letter, I know that's the end of that letter, and I'm ready to start a new letter. So we got 12 bits instead of 16. And the person understands the message. Okay, so this algorithm, coming up with the minimal set of bits to encode a lettered message, sometimes referred to as Huffman codes. Does that name come up in
Yeah,
Algorithms class, or which class?
networks class.
No, okay, data compression, okay. Is that what it was used for, data compression?
Yeah.
Okay, so here's another example, but I actually chose this example because this is exactly the way IP4 works. So suppose you were sending a message, and the message is A, B, A, C, blah, blah, this message, and it uses 5 letters, A through E, right? We have an E here, we have a D here, a C, a D. A through E is being used. Okay, so, just using bits, we could say, okay, log base 2 of 5, we need 3 bits to uniquely identify 5 different letters. So we could say 000 is A, 001 is B, 010 is C, 011 is D, 100 is E, and then the next 3 are just not used. We don't, 3 bits, we're allowed 8 letters, but 3 of them are not used. Okay, so we could send this message, 3 zeros is an A, 001 is a B, and so on. We send 48 bits. Suppose you, once again, we're going to use the idea of counting up how frequent the letters are, and we're going to try to use, for the letters that are very, very frequent, we're going to hope to use less bits than 3. For letters that are very infrequent, we're okay with using more bits. We could even go as far as using 4 bits for letters that hardly ever come up, and that still might be an improvement. So we observe in this message that 50% of the letters are A's, 25 are B's, 12 and a half are C's. This should be, sorry, 6.25 for both of them. 6.25 for both of them. So I'll change that later. So this should be 6.25 and 6.25. Okay. So with these percentages, is there some way we could, once again, send less bits? So we're going to use kind of the same idea as the last time. We're going to build this tree again. And we're going to notice that since 50% of the letters are A's, we're going to let the number 0 represent an A. And if the first number is a 1, what does that mean?
B.
No.
It's not A.
Not A, right? All we know is it's not A. Now, so if the first letter is since 50% of the letters are A's, we're going to let 0 represent an A. If the first character is 1, that means it's not A. Now, out of everything else, we have 25%, 12 and a half, and 6 and a quarter, 6 and a quarter. So once again, we're going to use the same, like inductively, say, okay, if the next number is a 0, that's a B, because this is a second highest percentage, 50%, 25%. And then if the first digit is a 1, and the second digit is a 1, what does that mean?
It's not A or B.
Not A, right. This one means not A, and this one means not B. Not B means, not A, not B means C or D or E. So if the next digit, since the C shows up twice as much as D and twice as much as E, we'll let 1 bit represent C's, and then this being a 1 means, if you see, if the character starts with 1, 1, 1, that means it's not A, it's not B, and it's not C. And then we'll let the 0 and the 1 decide whether it's D or E, right? So now we can send the same message using these codes. So these are the digital codes for those letters, and sometimes these are referred to as Huffman codes. We're trying to get the best percentage of numbers so that we have the minimal number of bits sent. So 0 is an A, 10 is a B, 110 is a C, 111, which means not A, not B, not C, 1110 is D, and 1111 is E. So now, instead of using 3 bits for every letter, we have 1 letter that has 1 bit, 1 letter that has 2 bits, and we have 2 letters that have 4 bits. This is actually worse than it was before. But we get such a savings up here, we don't mind this one. So now we can send the same exact letter, same exact message with a 0 and then a 10 and then a 0 and a 110 and so on, and now it only takes 30 bits to send the message instead of 48. And as long as the person who receives the message has this chart, they can decode the message. So the reason I came up with this one, I just came up with a string that would have these percentages, is because the IP4 addressing scheme uses exactly that. What they decided to do is classify, all the IP addresses will get divided out into groups. And basically the idea was, if you have, let's say, an entity like a university or a company, and you needed so many IP addresses, they would let, you know, some batches, some groups would get a bunch of them, and some would get a smaller amount. And the ones that would get a smaller amount, there would be more of those types of networks. So for example, they decided to have a Class A. They're going to let 50% of all IP addresses be Class A IP addresses. And what they'll do is for the first 8 bits, if the first bit is a 0, it's a type A. And if the first bit is a 1, that means it's not type A.
Okay.
Or it's B or C or D. Same idea as the last example. So I just copied, you know, the way they did it for the message that we sent in the last example. Type B's, 25% of the IP addresses are Class B. And what it basically means is the first bit is a 1 and the second bit is a 0. Now, and then so on for the type C's, the first bit is a 1, the second bit is a 1, the third bit is a 0. And type D and type E is 1110 and 1111, just like the last example. And then depending on what your use is, you would decide which one to pick. So Class A IP addresses, the first 8 bits is dedicated to identifying the network. And then the last, in this case, would be 24 bits. Host, host, host means 8 bits plus 8 bits plus 8 bits. 24 bits would be dedicated to you. So if you're the network, you can now give out 2 to the 24 unique IP addresses. So you would do this if you had like a really, really big company or university that needed to give out that many IP addresses. If you have a type B IP address, then, well, let me see if I go through each one individually. Okay, yeah, first of all, so a subnet, which is short for a subnetwork, is once traffic gets routed to your network, you then have the ability to assign individual machines in your company a unique IP address. So that would be called the subnet, the part where once it gets turned over to you, you could assign them however you want. So, type A IP addresses using version 4, IP version 4, are the ones where the highest order octet, the first 8 bits, are between 0 and 127. That's a type A. A type B is going to be where the first 2 bits are 1 followed by a 0. So that would be numbers 128 to 191. The type C's start off with 110, which are the numbers 192 to 223. The ones that start off with 1110 are type D's, and those are numbers 224 to 239 in decimal. And the 1111s are the 240 to 255 numbers. Okay. So you would think for the type A, so the number of type A networks in the world would be how many? If the first bit is dedicated just to indicate that it's a type A, and then the next 7 bits tells you
2 to the power 7.
2 to the power of 7. And they use a convention that they generally don't use the all zeros and the all ones. That's kind of reserved for use within your network. So really, you might think it goes from 0 to 127, but they're actually using numbers 1 to 126. So if the high order bit is 0, the values are between 1 and 126. So there's only 126 type A networks in the world. And the format is the first 8 bits represents the networks, and then the next 24 bits is the host. And what we'll call the system mask is if you wanted to just know what is the network ID, you only care about the bits on the network name. So if you anded these bits with these bits, the result would be just the network number. So the number of networks in the world is actually 2 to the 7 and then -2 because the all ones and the all zeros are reserved for special use. How many different hosts can we have? We have 24 bits, so that would be 2 to the 24, again, minus the 2 for all zeros and all ones. So there's this many, so if for example, you had a company and you were given a complete type A network, you could assign over 16 million individual IP addresses to people at your company. So that would be huge. Okay. The type Bs are the ones where the high order bit starts with a 1 and a 0. 1 meaning not A, 0 meaning B. It's a B. Okay. So now we have, that means the first 2 octets represent the network, and then the last 2, or the last 16 bits, represents which machine on that network. So, how many different type B networks are there in the world? Well, we have to use 2 bits just to identify it as a type B, and then the remaining 14 bits tells you which network of type B it is. So that would be 2 to the 14, once again, -2. Right? The all zeros and all ones, of special use. So the world has 16,382 type B IPv4 networks. And on each of those networks, we now have 16 bits. So 2 to the 16 -2, we have 65,000 different machines on each one of those networks of a type B network. Okay, so just, we kind of get this idea. The type Cs are the numbers where the decimal value for the first octet is between 192 and 223. The high order bits are 1 meaning not A, 1 meaning not B, and 0 meaning C. And now we use the 24 bits as the network number. But we had to use up 3 of them just to say it's a type C. So it ends up being 2 to the 21, again -2. So there's a little over 2 million type C networks in the world. Okay. And then on each one of those, we have 8 bits to decide which machine it is. So 2 to the 8 -2 is 254 unique values we can assign. Okay. So now what we'll call subnet mask is where we're saying, okay, if we AND your IP address with 11111 and then all zeros, what will come out is just the type A number. This would be the type B mask, and this would be the type C mask. You just wanted to know what the IP number was for routing. Okay, so now if we wanted to route data around, and if an IP address like 192.168.1.254, if a message was being sent to that IP address, so the question would be, first of all, what is the IP address? What type is this one?
It's class B.
Is that right? Let's see. So no, 192 to 223 would be type C. Okay, so it's a type C. And so suppose that the type C comes in, and because this is type C, and then it goes to the third octet is a 1, so it gets sent to this router. Those bits get ORed together, and it gets sent to this router. And then we have machine 1 and machine 2 connected to this local area network. So we can have a message get routed to a particular machine. And then if the second one was a 2, it would get routed to the LAN connected to number 2. Okay, so now as far as, who gets to give out which IP addresses, the IP addresses are kind of divided up around the world, and So it's basically a map of who the authorities are to give out IP addresses throughout the world. So they're all kind of parceled out and given to different parts of the world to give out. Okay, yeah, so here's just a little bit of a recap, who's giving out the addresses and how many bits are used. And then, again, here's the subnets again. So you would use, you know, the subnet address, and then you could figure out, you could calculate what the bits are for the network just for routing purposes. And what we talked about earlier in the course, when we were addressing memory, computer memory, we put an address in the MAR, and it made us turn off every piece of memory except the one we wanted to write data to. Well, this is going to be the same idea. We're going to write to, instead of writing to a piece of memory, we're writing to a machine. So you kind of take, after you've masked out the IP address and you get just the network number, you're routing to that particular node on the network. Okay, so now the idea is this. Why, I guess one of the questions is, why have we not run out of IP addresses? There's only a little over 4 billion, and there's almost 7, 8 billion people in the world, and everybody has multiple connections to the internet. Now cars are connected to the internet, and cell phones are connected to the internet. But there is one thing we can do. We could use a technique, and we'll talk about this more when we talk about routing. But the idea that each machine isn't assigned a dedicated IP address, it could be assigned an IP address every time you connect to the internet. And we say, okay, let me give you one of our IP addresses. So let's say, for example, you have a company, and your company has one Type-C network, because that's all you can afford at the moment. So Type-C, if you remember, Type-Cs have 254 IP addresses that you could give out. So let's say you have a Type-C address, okay? And you have 1,000 computers or faxes, you know, different machines at your company that you need to give an IP address to, but you only have 254, the world allows you to have 254 IP addresses, but you have like 1,000 machines to give an IP address out to. So the question is, what can you do about this? So one thing you could do is you can buy 3 more Type-C networks, right? And then you'll have this number times 4, which would be 1,016. Which would be, you know, enough to cover your 1,000 computers. But then if you bought some more computers, you need another one. So one thing is to just buy more Type-C networks. But another thing we could do is we could dynamically assign the 254 IP addresses we have. And the way we would do that is, okay, your company has, you know, one Type-C. Okay, so what you could do is we can take our 1,000 devices that we have and create an internal table. Just number them 1 to 1,000, all right? And then what we do is every time one of them wants to connect to the internet, we take our 254 available IP addresses and we bond one of them to the machine. So it would be something like we would keep a table. So let's say all our internal devices had numbers between 1 and 1,000. And then these are the IP addresses we have. Let's say, for example, we were given 192.181.16. That's our Type-C, and then we get to fill in the 1 to 254 out of here. So we're given the numbers 192-181-16.1 to 192.181.16 to 254. We have those IP addresses which we own. So if device 341 inside our company wants to connect to the internet, we assign 192.181.16.1 to that one. Now another guy wants to connect to the internet, we assign the next one. So what we could eventually do is we could give out 254 numbers to all the computers in our company. But I guess once the next person wants to connect, the 255th, we're out of IP addresses to give out. So, okay, so this is a way, what we could do is we could just have our internal firewall assign internal numbers to external IP addresses and give them out. So now the question is, could we allow two internal devices? So it looks like we kind of have a high watermark, like a number if we hit, then we're stuck. Is there a way we could use the same IP address and connect two devices to the same IP address?
No, can we revoke the IP address of the first and give it to the second one?
Well, we can only do that once it's done. Like, let's say this is a machine that is connecting, you know, someone's connecting to Facebook and they're playing around at lunchtime and they're going on Facebook, right? So as long as they're connected to Facebook, Facebook needs them to have a dedicated IP address to send messages back to. If they log off, then this one becomes free and we could use it again. But let's say all 254 of our Type C IP addresses are used up, and a 255th person wants to connect to the internet, and we've used up all our IP addresses. Is there a way we could use the same IP address, like 192.168.1.16.1, and allow two computers to use it?
Yeah, we can pack the port number with it and we can send it to them.
Well, yeah, but the other thing is, yeah, but even we could do that a step further if we want to use port numbers. But one thing we could do is we could just say, okay, if one user is logged into Facebook using this IP address, they're going to send messages to the Facebook server, which has a unique IP address. And when it replies, we know who the reply is from.
Yeah.
So we could say, oh, if the reply is from Facebook, it goes to you, and if the reply is from, let's say, some other employee is logged into LinkedIn, and they reply, LinkedIn replies to them, we send the reply to them. So we can actually go even a step further. We can have multiple internal computers sharing the same IP address, as long as they're talking to two different servers. And then we can even inside the messages who you logged in as, we could even break it up further if we wanted to. But as long as they were talking to two different machines, we would be okay.
Is this possible in real world, Professor?
Is it possible what?
In real world?
In the real world?
Yeah.
No, they do that. Companies do this.
Oh.
We do. Actually, what's really strange here at the university is all of the IP addresses are not dynamic. Every machine at this university, oddly enough, has a unique IP address, which is kind of strange. But I'm sure, do you have internet at home?
Yeah.
Do you know who the internet company is? Comcast? Who do you have? Optimum Online? Okay, so when you log in, it's very likely they assign an IP address from a pool. And if you logged in next week, you might have a different...
Yeah, it changes.
Yeah.
It changes, right. So what they're doing is they have a pool, and then every time you log in and out, they assign a number to you. They kind of do that for two reasons. One is they can let more, they don't need as many IP addresses to handle all their clients. And then number two is, if you wanted to run a business off of your home account, you'd have to buy a URL like www., whatever your name is, .com, and then you'd say that is equal to an IP address. Well, as long as they keep changing it, you won't be able to have that name mapped to your machine. So if you want to run a business, they want you to pay extra, and then they'll give you a dedicated IP address that will never change. So yeah, so companies do this dynamic IP address assigning. So for example, we could, let's say we got to the point where we got up to 254 and then another person wants to connect to the internet, we don't have any more to give out. We could have, device 123 is connected to 254 and it's talking to Facebook. And 456 is also using IP address 254 and it's connected to LinkedIn. And then whoever the messages are coming from, do we just route them to that person?
But if both of the devices want to access Facebook, the same server, they won't be able to do it.
Right, so that's, yeah, so that's good. Now you're following this. So Facebook has many servers. If you look up what Facebook's IP address is, and then look it up again, you might actually connect to a different machine. But if you happen to be talking to the same machine, well, if you're talking to two different versions of Facebook, as long as it's two different machines, we can tell from the port, we can tell from the IP number, it's a different conversation. If they happen to be on the same machine, they're also replying with a port number, and if the port numbers are different, that means it's talking to a different person. So, for example, let me bring up the command window. So the command window, this is, I think we talked about this in another class, right?
Yeah. we
So
did.
this would be like what what Microsoft
Command
DOS,
prompt.
disk operating system looked like, back in the 80s when you bought a computer. But anyway, the ping command still exists. So if we say ping,
It's wrong, Professor.
Wrong.
it's wrong?
If we
Oh, okay. Can't even zoom in. So I'm pinging, which is just sending a message. I'm sending a message to the Facebook server, and just to see if it's alive. If it's alive, it'll reply to us. But when it replies, it gives its IP address. Right. So, their IP address. Write this down. You have a pen, or could you write this down? So their IP address is 31.13.71.36. So what type is that? That's a type A, right?
Type A.
Wow. Type A. So I doubt, that can't be. I doubt they own the whole 31. Someone else owns it and they bought part of it. But, okay, so anyway, so if I was to bring up a web browser, and I was to go to http:// what was it, 31 dot?
13.71.36.
So it's 31 dot what?
13,
13,
71,
71,
36.
36. So if I just go to that IP address, hopefully it goes, yeah, it goes right to Facebook. So instead of using the nickname, www.facebook.com, which then goes looking up a table for an IP address, I just went straight to the IP address. So the message I sent, so if from your seat, if you do ping on Facebook, do you get the same number or a different number? Does anyone get a different number? A different IP address? So if you bring that up, what, if you
The
bring,
same one, please.
you get the same one? You get a different one? So if you go, yeah, CMD, and then just ping, and then www.facebook.com.
31.
Yeah, all right, we're all connecting to the same one then. Okay, sometimes they come up different. Because they have, not only does Facebook have many servers, they also have the old style, the IP4 and the IP6. So, okay. So for example, you guys shop on Amazon.com. So they're also a 54, they're also a type A. So the thing is, you could probably Google who owns, so remember, type A's are numbers between 1 and 126. The first, if the first, the first octet is between 1 and 126, that means it's a type A. And there's only 126 in the world. So I doubt Amazon owns the whole 54. Whoever owns 54 is probably selling pieces of it out to Amazon, pieces out to Facebook and that kind of thing. Okay, so yeah, so that was really, I just wanted to go over, it's really the concept of IP addresses. I think that version 4, the 32 bits, is kind of easy to follow. That we kind of had to deal with that annoying, what the initial bits mean. That if the first bit is a 1, it's a type A, and if the first bit is a 0, it's a type A, and if the first bit is a 1, that means it's not type A, so you have to look at the next bit, or next several bits to figure out if it's a B, a C, a D, or an A. And then however many bits you used up to figure out what type it is, then you get the remaining bits to figure out what the network is, and then however many bits are left over is how many hosts you have. But then we can play tricks by assigning many, many machines through a small number of IP addresses, which is really the reason we haven't run out of IP addresses, because we could assign many machines to one IP address. Well, we're getting close to running out. So there'll be a new, the new system coming out is IP version 6. Uses 128 bits. Like I said, you would think just if they added 2 more bits, we'd have what, 8 billion, 16 billion. That should cover us for another decade. But they wanted to make routing much, much faster. So more bits we use just to route packets to the network it's going to, and then once it gets inside, it's easier to route. Yeah. So they made the IP address 4 times bigger, but it'll help routing a lot better. So maybe we could talk about the new format in the class towards the end of the semester. But it's really more important just to get the concept across.